Welcome back everyone. So we will continue from Bohr's model. We have discussed the three postulates of the Bohr's model, right? So in this part we will discuss the application of the Bohr's theory. Okay, so this discussion is also very important, because from here there are lots of questions in different kind of exam is different kind of asked. Basically lots of questions are from this part. This is totally mathematical calculation, we can say, but let us start. So we know the condition for which electron can revolve around the nucleus, that means in the orbit. Okay, that is the mvr equal to nh by 2 pi. If this condition is followed, then only electron can evolve around the nucleus. Okay, so this is called the stable or stationary orbit. We know that, but we need the explicit form of the radius Rn, right? Let's say. So let us do the calculation first. So let's consider any nth orbit. Here this n is the principal quantum number which indicates the orbit, which orbit it is. If it is 1, that means like this, there may be n number of orbit. For here this is n equals to 1, n equals to 3, n equals to 3, 2, 3, like. Okay, let me say it also here clearly. This is the nucleus, this is the first orbit where n is equal to 1. This is called orbit K. Okay, let me check whether it is small k or big K. Okay, this is the big K, so we should write it. Okay, let's say these are totally spherical, okay, circular orbits. Due to human error it can looks like elliptical. This is called orbit L. N is for n is equal to 3. This is called orbit M. So it's N, O, and so on. There is no restriction, because here n is integer, it goes up to infinity. There is no restriction basically. It may be 1, 2, 3, 4, 5, it goes up to infinity. But in practical case we will see that there are some finite limit. Why? That we'll discuss in detail those things. Okay, so these are for n equals to 1, we can say mv1 r1 should be equals to h cross. Here should be mv2 r2 equals to 2h cross. Like things. Okay, so these are the quantum nature. Quantum means the discrete. We have discussed all what does quantum means, right? In the dual nature of radiation and matter part, we know these are not the new terms. Okay, so this is the orbits. So let's consider any orbit, that is the nth orbit in general. Okay, so nth orbit, this should be followed, otherwise electron will not. What happens? Otherwise electron can't form the standing wave and it will be collapsed. So it should be fall in nh cross, let's say. NH cross. We can also write nh by 2 pi, h cross and nh by 2 pi is the same thing. N is equal to 1, 2, 3, 4 and so on. So what we can write from here? Vn, that means velocity. Okay, this is the Rn, this is the Vn. Okay, and mass of the electron is m. Vn is nh divided by mrn. So if we square it, then we can write it. Okay, v square is this. Now here we discuss now these things should follow. That means centrifugal force should equals to centripetal force. These force should be equals to each other. Otherwise, electron can't be stable. From classical mechanics, we know these things. This is pure classical result. So we can use those result also, because that should also be followed. Otherwise, electron can't rotate around the nucleus. Okay, classical mechanics gives this result. So we can write it for nth orbit in general. We can write it m Vn square Rn equals to 1 by, from electrostatic. So we know this is the Coulomb force, Rn square in general. So from here also we can write Vn square is equal to 1 by 4 pi epsilon Jd square by mRn. Yes, if we now we have to equate these things. So it should be equals to Jd square by 4 pi epsilon. Epsilon naught is used because we are considering the vacuum, and also in atom, inside atom, we know that there is in center there is nucleus, and around nucleus electrons are revolving, but between electron and atom, electron and the nucleus, there is nothing. That is the ultimate space, free space, vacuum we can say. So that must be epsilon naught. Okay, and here is mRn. So now if we equate, then what will happen? N square h cross square mRn is equal to Jd square by 4 pi epsilon. So now Rn will be 4 pi epsilon naught n square h cross square m Jd square. Yes, if we put h cross is equal to h by 2 pi, then it will be h cross square and 4 pi square. So 4 pi will cancel out, there will be only pi. Okay, so this is the radius of the Bohr, nth Bohr's orbit. So this is the correct. So this is the radius. We know these things. Now we have to find out the total energy. The energy of when the electrons is circulating in this orbit, what Bohr said? Bohr said that energy will be constant. That means that energy will be invariant over time. It will not radiate any energy. The energy will remain constant. So we have to calculate that energy. Okay, the energy of the Bohr orbit, nth Bohr's orbit. Okay, so what will be the energy? It will be Ek, that means kinetic energy, plus Ev, that means the potential energy, or Ek or Ep, kinetic and the potential. Okay, so what is the kinetic energy? We know that must be half mv square. This is straightforward. As it is the nth orbit, so we should add n. So let me write it like this: nk np. So this is nk, then it will be okay, general case. And what is the form of Vn? Here is the form of Vn. So there are two forms, but we need to put the value of R. Okay, so Vn is actually nh cross divided by mRn. So nh cross m. Now Rn is epsilon naught n square h square pi m Jd square. So what will be the case? N h, we can write it nh by 2 pi. So if it is, then here is also n square h square, then square will goes away, pi will cancel, will cancel, So it will be Z square divided by 2 epsilon naught NH. So this is the Vn. So if we put it, then it will be half m Z square and 2 epsilon naught NH. So it will be, okay, m must be there, right? Here must be 1 m. Here must be 1 m, I think, half m square. Okay, we can take this equation. Also, this is correct, this is not wrong, okay, but also we can do it like in the following way. Okay, we have the information of Vn, this equation we know, right? So we should Z square 4 pi epsilon naught mRn. Ultimate result will be same, there will be no change, but let me follow the standard procedure. So it will be 1 by 4 pi epsilon naught Z square by 2Rn, correct? So this is the E and K kinetic energy. Here Rn is not, we have not put the value of Rn. If we put this value, then eventually we obtain the previous result. That was not wrong essentially. So but we have to consider the potential energy also. We know how we calculate the potential energy in electrostatics. If there is some positive charge, let's say this is some Q charge is there and unit charge is coming in the field, electrostatic field, then the potential energy will, V is calculated like this, na? The force F dr, R is tends to infinity to R, like these things, right? So if we calculate, what will be the F? F will be Z square by 4 pi epsilon R square dr, right? This is the force, this is the force, electrostatic force. We have discussed these things in electrostatic chapter. So let me write it. So Z square 4 pi epsilon naught will be out, there will be 1 by R square dr, limit is infinity to R. So it will be Z square by 4 pi epsilon minus 1 by R. If we integrate this, then we will obtain minus 1 by R, infinity to R. So it will be minus Z square by 4 pi epsilon naught R, and let's say if it is R, then we should put it R prime. Here R prime is the dummy variable. Okay, so then it will be R, and if we put infinity, then overall term will be 0. So this is the potential energy. So EP should be equals to minus 1 by 4 pi epsilon naught Z square by Rn, correct? Okay, so total energy will be, we have to sum it. So it will be 1 by 4 pi epsilon naught, if we add it, minus Z square by 2Rn. So this is the total energy. So it is the total energy of electron in nth orbit. So from here we can write it, we can see here that En equals to minus Enk, and also En equals to twice not half of Enp. Okay, so these are the results. So now this is correct, but now we have to put the value of Rn. So now then the final result will be En is equal to minus 1 by 4 pi epsilon naught, this is Z square by 2Rn, and now we know the value of Rn, this is the Rn, epsilon naught n square is square by Z square. So we have to put it, so it will be 2. So for Rn, let put it pi m z square divided by epsilon naught n square h square. So it will be minus m, pi will cancel only, okay, then z square e to the power 4 divided by 8 epsilon naught square n square h square. This is the form of En, final expression. Okay, so this is the energy. So for hydrogen atom, what will be the energy? En for hydrogen atom, it will be En for hydrogen atom means Z equal to 1. We have to just put Z equal to 1, then it will be m e to the power 4. We will discuss in details in next class for hydrogen atom case, but let me stop here. This is the general expression of the energy. So let me revise from the beginning what we have discussed. That first we have discussed the Rutherford model, then the drawbacks of Rutherford model. After that we introduce the Bohr's model. First we have carry forward the Rutherford models, carry forward the outcomes of the Rutherford models. These are the things, and then we discuss the postulates of Bohr's model. There are basically 3 postulates. So that's why it's called, as these postulates are totally inconsistent with the known classical mechanics, that's why it's called the revolutionary, because otherwise we can't explain the results, experimental results, as the atomic spectra or other Rydberg constant like things results are. But that's why you have to consider this model, though it is inconsistent with the classical mechanics, but it gives us the right result. So that's why it's very important, very, very important. It's actually groundbreaking in discovery of quantum mechanics. Okay, so these are the postulate. First postulate all about the stable orbit or stationary orbit. Then we discussed Bohr's frequency condition, and from here also we can directly understand that as there are some restricted orbits, some specific orbits are there. So eventually there must be some specific transition between these orbits, otherwise there will be no scope of scope of exchange energy. Only energy will exchange or radiation will exchange only when the transition occurs. That may be excitation, maybe de-excitation, but otherwise there will be no exchange of energy. So that means as there are some restricted radius are allowed to rotate around the nucleus for electron, so energy of those orbits are also fixed. We know this, we have also discovered the form of the energy. So essentially there are some fixed transition. Okay, so there will be some fixed wavelengths in the atomic spectra, specific wavelengths. Essentially there will be no continuous spectra, because we have already discrete the energy levels by restricting imposing the restriction on the R. Okay, we will discuss these things in next class, but this is the Bohr's frequency condition. Then we discuss the most important things, Bohr's quantum condition, which says that which radius will be allowed as the Bohr orbit. Then we give some justification from de Broglie hypothesis behind this postulate. After that we discuss the application of Bohr theory. We evaluate the form of the radius of the, okay, we discuss the radius of the nth orbit, any nth orbit which is like this, which is called the Bohr orbit, and we have also evaluated the form of the energy of that nth orbit, total energy. This is like this. Okay, in next class we will carry forward from here and we will discuss for hydrogen atom, and then we will discuss the atomic spectra. So thank you for staying with me. Thank you all. Meet you in the next class.